In the second half of 5.3, we're going to take a look at the half-angle formulas and the power reduction formulas. First, let's talk about the power reduction formulas. What this can help us do is to rewrite a statement where we've taken it down by a power of 1. So you'll notice here we've got sine squared, cosine squared, tangent squared. This reduces it down to a cosine to the first power. When we don't have anything written there, we assume it's being raised to the first power. And this can help us rewrite statements involving sines, cosines, tangents that are not being squared. So we're going to use this power reduction formula, and we're going to use it to reduce a cosine that is being raised to the fourth power by using the same thing multiple times. So we're making repeated use of it. So let's take a look at how we can do that. If we start off with cosine to the fourth x, let's put this in terms of the squared, because the squared is what the formula is based on. So cosine to the fourth power obviously could be reduced to cosine squared x squared. So we're squaring the square of the cosine. And now that's in the form that we can use, so just pulling out the formula, we have 1 plus 2 cosine x, or 1 plus 2, put the 2 in the wrong spot there. Let's fix that. So 1 plus cosine of 2x, meaning we're going to double the angle, and then all of this is divided by 2. This, of course, is being squared, so let's go ahead and not forget to put that in there. Now we can apply the squared here. I'm going to rewrite it with the top part squared, just kind of separate it out, because I want to remove the more complicated part of this here, which is the 2 on the bottom. So that 2 squared can become a 4, and this is still being squared on top, just kind of partially reducing it, so I can rewrite this as 1/4 times 1 plus cosine 2x. This is just going to allow us to focus on the more difficult part here without having to worry about the fraction. Okay, so, and of course, dividing by 4 is the same as multiplying by a 4th. Now let's go ahead and square this, which means we have to actually take the binomial and multiply it by itself. So 1 plus cosine squared x, cosine squared 2x. Oops, I wrote that 2 a little too small there. It looked like a squared. So let's fix that. So cosine 2x, which means we're doubling the angle before we take the cosine of it, and we'll just multiply it by itself. And now we're going to apply our tried and true, and we have the 1/4 here, FOIL. So let's FOIL this out. And so 1 times 1 gives me 1, and all of this is going to be multiplied by 4, so I'm going to keep this parenthesis here. And then 1 times cosine 2x, which is just cosine 2x. And then we end up doing the same thing here. We get a plus cosine 2x again. And then we have cosine 2x times cosine 2x. So that's plus cosine squared 2x. All of that multiplied by a 4th. So again, here, this is where we can take this part out. These two can be combined together. We're not going to take that out. We're going to rewrite it using, again, the power reducing formula. I still have this 1/4 out here. Don't forget about that. But then we have 1/4, 1 plus 2 cosine 2x. Cosine 2x plus cosine 2x gives me the 2 cosine 2x. And then we have that plus cosine squared 2x. And this is the part that I'm now going to rewrite again. So now we need to apply the power reducing formula a second time. Notice how when you do stuff like this, you want to just keep rewriting as much as possible. Do one step at a time. And so we'll apply this again. And let me write this down here. Just what the cosine squared x formula was. This was equal to 1 plus cosine 2x over 2. So notice that this part here is just a single x. What I have up here is a 2x. We can still apply this formula. Just keep in mind that this angle is turned into 2x up here. So if I have 2x there, I end up with 2 times the 2x. So in other words, we have to, since we're doubling this x, where this is only one of the angles and then this one is doubled, whatever angle I have here is going to be doubled. And so I end up with 1 plus cosine 4x, or 2 times 2x, which is 4x, all over 2. And of course, we have the 1/4 there as well. Let's rewrite this part so that it's not one big fraction, but we'll take the 2 into the 1 and into the cosine of 4x. So in other words, I still have this 1/4 there, still have the 1 plus 2 cosine 2x, plus we end up with a half here, plus 1/2 cosine of 4x. We can combine the 1 and the 1/2 here, but we cannot add these two together because they are not like terms. But the 1 plus 1/2 gives me 3/2. So I have 3/2 plus 2 cosine 2x, plus we added this, so that's back here, plus we have 1/2 cosine of 4x. Now for our final thing, we've got a number term. All of these terms are different. They cannot be added. So we just can distribute that 1/4 to have our final formula. So this would be 3/8 plus 2/4, which is 1/2, cosine 2x plus 1/2 cosine 4x. And that is my now identity. We have kind of created another formula, if you will, for a cosine to the 4th x. So this is equal to cosine to the 4th of x. So for any cosine raised to the 4th power, we could just plug it right into this formula and get our results that way. So it utilizes a double angle and an angle multiplied by 4. Let's take another look at rewriting a given expression so that it doesn't have a power greater than 1, so that it's just as simple as it can be. So first of all, let's rewrite sine squared. Going back to check our formula, that we see sine squared x is 1 minus cosine 2x over 2, or cosine squared x is 1 plus cosine 2x over 2. Here we're looking to multiply them. So rewriting the sine squared x, we'll put it as 1 minus cosine 2x all over 2. And then we'll rewrite the cosine squared as 1 plus cosine 2x all over 2. Because we're multiplying, we can just go straight across on bottom. So now we have a 4 down here. And on the top, we have 1 minus cosine 2x multiplied by its conjugate. If you notice, these are conjugates of each other. And those, whenever we have conjugates being multiplied, we get the difference of two perfect squares. The middle terms in our FOIL end up canceling out. You can see that right here. This will give me negative cosine 2x, and this will give me positive cosine 2x being added. They become 0. So we're just left with the 1 times 1, which is 1 squared, and cosine 2x times cosine 2x, which is cosine squared 2x, and this is all over 4. That means we're not quite out of the woods here yet, because we still have a cosine squared 2x. So we're going to have to apply it one more time. Again, I'm going to pull out that denominator of 4, so we can just focus on the 1 minus cosine squared 2x and rewriting that. So again, keep in mind that the formula we have is for just cosine squared of x, and I have a 2x here. So if I'm going to apply this and make this into 1 minus, or sorry, for cosine it's 1 plus cosine of 2x, cosine of 2x, and we have a 2x, that means I'm going to have to take twice 2x when I substitute it. This is all over 2. So we want to take 2 of 2x, right? That becomes 4x. So rewriting this again, I have 1/4, 1 minus, and for now I'm going to keep the fraction there, 1 plus cosine of 4x all over 2. And we can break this up. If I do, the sort of reasoning there is I've got a 1, and if I break this up, I have a 1/2. And that means we can simplify it, and it'll give us something slightly simpler. So I'm going to write 1 minus 1/2 plus 1/2 cosine 4x. So I took the 2 under the 1, basically to both parts of that plus sign there. So now I can combine these two together. 1 minus 1/2 is 1/2. So I have 1/4 times 1/2 plus 1/2 cosine 4x. And then distribute the 1/4. That leaves me with 1/8 plus 1/8 cosine 4x. Another way to write this as a single fraction is just to write 1 plus the cosine of 4x all over 8. Either of these are acceptable. One is not a simpler version of the other. This is writing it as just a single term, where this is writing it as two separate terms and basically distributing that division by 1/8. Let's take a look at, in the first half we looked at double angle formulas. We also have half angle formulas that we can use. So if we have some sort of angle that we know is half of a known angle that we know, the 45s, the 30s, the 60s, the 90s, 180s, those type of angles where we can get exact outcomes, and we know something is half of that, we can use this to rewrite it in terms of the angle that we do know. In other words, we're able to put it into exact form as opposed to like an approximate form. How do we get to these half angle formulas? Well, let's take a look at cosine. Let's start off with our power reduction formula. So we have cosine squared of x. We know that is equal to 1 plus cosine 2x, or I'm just using theta, all over 2. And let's take a look at what happens if we substitute there theta over 2 in for our theta. So every theta is going to be a a half. So if I rewrote this top part here, we have 1 plus cosine 2 of theta over 2. And of course, this is all over 2. And so we're taking the cosine of this 2 times theta over 2, but of course, 2 times a half gives us 1. So this simplifies quite a bit here. It gives me 1 plus cosine of just regular theta all over 2. And if I wanted to get this down so it's not a cosine squared, we just take the square root of both sides. Remember, this is cosine of theta over 2, and then it's squared. We have that squared part in a weird spot, but the reason we do that is because if it was over here, it indicates that we're squaring the angle before we take the cosine of it, and that's not what we're wanting to do. So when we use the squared there, we always put it next to the cosine, indicating take the cosine first and then square that result. When I take the square root of both sides, we get cosine theta over 2, and we get our formula is equal to the square root of 1 plus cosine theta over 2. And this is the half angle formula. Let's go back to that screen. You see it is this. And plus and minus, I should have included that as well. Whenever we take the square root of both sides, the square root of both sides, of course, gives us a positive and a negative. Those will depend on what quadrant theta over 2 is in. And we know that sine and cosine can both be positive or negative depending on which quadrant we are talking about. So both the sine theta over 2 and the cosine theta over 2 end up, as we saw earlier with the power reducing ones, in terms of cosine. And then tangent actually has 3 different formulas that are similar, produce the same results. Positive or negative, this one, or this one. And the plus or minus depends on which quadrant theta over 2 lies. So we want to look at what that angle is before or after we've taken half of it. So here, taking the cosine of 157.5, that's like an angle we've never seen. It's not an angle that we would normally think of in terms of it being like one of those known angles that we have. But it is. If we double that, we could rewrite this as cosine of 315 divided by 2. So notice that the theta there is 315. When we're expressing it this way, of course, 315 over 2 is the angle I'm taking the cosine of, but it's theta over 2. So the theta we can use then when we rewrite this, and let me go ahead and just write that in. 315 is in the 4th quadrant, and cosine is positive, so I'm going to include the positive square root here, and that's 1 plus cosine theta, our theta being 315, which has a reference angle of 45 degrees, being in the 4th quadrant. And so 45 degrees, we know the cosine of that in the 4th quadrant, it is positive, so this becomes 1 plus square root of 2 over 2 all over 2. Or you could rewrite this as, I'll give myself some room here, square root 1/2 plus 1/2 times root 2 over 2. Just taking that 2 to both parts here, multiplying by 1/2, or dividing by 2 is the same as multiplying by 1/2. And so let's rewrite that again, simplify, go ahead and multiply these together. That's the square root of 1/2 plus root of 2 over 4. And if we put in, get a common denominator here, multiply the top and the bottom by 2. That gives me a common denominator of 4, so that's the square root of 2 plus root of 2 all over 4. The 4, whenever we have a square root of a fraction like this, square root of a over b, we can take the square root of a and the square root of b separately. And I'm going to go ahead and do that here just to simplify the bottom, which is a perfect square. So we have a little bit of an awkwardness because we have a root under a root, but that's okay. We're just going to write as 2 plus root of 2, square rooted, and that's over 2. And now we have put this into exact form rather than having it be in approximate form. And that's good because whenever we approximate things, and that generally has to happen with square root of 2 is an irrational number that repeats forever without a pattern. And so this leaves it in exact form without us having to approximate by rounding it. So basically as we approach these types of problems, you're just going to practice using that. But in general, we want to open our eyes a little bit to, hey, is there a way for me with this angle that is like one of those unknown angles? Is it half of something? So if I double it, will it be one of our known angles that we have? Or if I were to take half of it, would it give me something that is a known value? And that's how we can use the double and the half angle formulas to simplify our trigonometric expressions.